Well, thanks again, Beatrice, for having me here to the wild north of flatland in Canada. Um, This is going to be two talks, and you'll heard some of this stuff before, because Joel gave an excellent introduction to an awful lot of what's contained within the Rietveld refinement method. But that's okay. Repetition is good in teaching. By the way, chemists, any chemists? Chemists? Anybody recognize that molecule? Anybody? Anybody with an explosive intent in their mind? That is, its formal name is pentaerythryl tetranitrate, nitrate. And something with that many nitrates tends to go off with a bang. So this is the high explosive PETN. It's a cool icon for GSAS-II, but it also is a sort of reminder of one of many hats that I've worn over the years. I wear a lot of hats because I get easily bored, I think is probably the best way to put it. Anyway, when I was at Los Alamos, one of the things that I did was to do high pressure studies on high explosives. And that was one of the featured molecules in an experiment to do just that. And managed to get it up to 10 kilobars, I think it is, and back down again. That's the key point, without it exploding. That was the second try. The first try, it exploded partway through. And the most amusing thing about this is that this happened at about the same time that I was tasked with going across the street at Lance and talk to the folks that actually ran the source. The guys who ran the proton accelerator and all that. And I described to them what it was I was doing, which was high pressure experiments on high explosives, and they all just laughed because it sounded so ridiculous. That's something that one could do. I might add that it freaked out the safety people because the high pressure people were freaked out by the existence of high explosives. The high explosive safety people were freaked out about me putting it under pressure. But nonetheless, the experiment worked. The interesting thing about it is that under pressure, this thing does a subtle rotation, which makes it more susceptible to decomposition by a shock wave that goes through. Hence, it explodes. Anyway, I'm going to talk about the Rietveld method, give you some history from my own perspective of how it all developed. A couple of extreme examples. One was Joel talked about, but I'll add a few more words to it, of the math, and go through a worked example that is actually forms one of the tutorials for GSAS-II. If I do this right, there we go. Hugo Rietveld, who's pictured right here next to his neutron diffractometer. By the way, in a high likelihood, the beam might have been on. It was a long time ago. The beams were weak and safety considerations are not what they are today. But he was a very nice man. And he wrote these two papers that described his method, which Joel gave reference to. And basically described what's now known as Rietveld refinement, which is a multi-parameter nonlinear least squares curve fit. The key thing to remember here is it's fitting to a curve. It's not fitting to individual structure factors like in single crystal crystallography or something else. It's fitting to the profile curve of a powder pattern. And it took a long time for people to accept that simple fact because there was lots of discussion about, well, how many reflections are there? Are these reflections unique? It doesn't matter a whit whether they are or not, because the reflections are not observed in a pattern diffraction experiment. What's observed is the profile. The reflections are part of the model. You just remember that. That has lots of implications as you go through trying to do crystallography with powder diffraction. Anyway, so the idea is you're trying to fit the individual intensities in a powder diffraction pattern by a curve which is composed of a summation of various heat intensities, each profile calculated crystal structure. You can define a simple residual, which looks an awful lot like the single crystal one, is simply the difference between the observed and calculated intensities squared, multiplied by weight, and then summed. And this thing right here, which is down here, is the actual thing that's minimized by these squares in a Rietveld refinement. This thing is known as the chi-squared in statistics. An awful lot of people will confuse it by calling this thing chi-squared. It's really the reduced chi-squared, where you take that and divide by the number of degrees of freedom. This number is somewhere in the vicinity of 1. This is just whatever it happens to be, some large number. And then the rest of the residual is then defined by dividing by the weighted observations squared. So you get an R value. This R value, by the way, is the only one that's really relevant for fitting in powder diffraction. Other ones having to do with Bragg R values are all derived from the model, basically, of the intensities for the intensities. Okay, that's the essence of it. Where did I fall into this business? Well, in 1972, I happened to be a postdoc at Oxford in England. And I was trying to do electron microscopy and not doing a really good job of it because my eyes weren't that good for adjusting the images to make them look good. So Tony Cheatham, is the AKC here, walked into my office one point and said, "Hey, Bob, how'd you like to do a neutron powder diffraction experiment?" I said, "Sure." And we chose to do, well, I'll talk about that in a second, but the place where we did it was just down the road from Oxford at the, let's see, it's Harwell Laboratory or something like that. Anyway, it was the English equivalent of Los Alamos, you might add. They had this reactor. The shell, by the way, is actually still there, but there's nothing in it. And this is the inside of it. And if my memory serves me correctly, which is not all really clear at this point, 50 odd years later, is that the diffractometer was down inside this pit. Because I remember that thing being swung around overhead. Anyway, this is what it looked like. It had a monochromator, and the thing that we decided to do is to back off the takeoff angle off the monochromator as high as it would go, which is up here someplace, and then scan on 2 theta. The experiments then were taken at 2 different wavelengths, about 1.5 angstroms. This is the flux, which is really small by nowadays. Each scan was at 50 minutes per degree. That means each scan was like 3 days long in order to collect the powder pattern. This is where we started with the code, which was Alan Hewitt's take on Rietveld's original computer program. Now, what Alan had done is he added anisotropic temperature factors to the original Rietveld model. And I had to mess around with this to get it to do the problems, which, oops. Did I miss something? Yeah. No, I'm fine. So it ran on this thing, which is the ICL 1906A, which is the English equivalent of an IBM 360 or something like that. Big old mainframe computer, which took up a room. You can sort of see it here. It's huge. This thing had a tiny memory, 256 kilobytes, and the words were 24 bits, which is a little strange, but that's the way it is. I always liked this as an American. This is the operating system was George III. And if you know your history, you'll understand why. This thing produced a megawatt of heat, which is enormous, and it has about as compute power as some people's smart watches or less. And there was a very similar one at Oxford on the Banbury Road, which is the one that I actually used. Okay, fine, thanks. So what did we do with it? Well, it was two compounds. One is titanium niobium, both titanium niobium oxide, TiNB207 and Ti2NB10029. These were so-called block structures that were very thin in one dimension, 3 angstroms or thereabouts, and quite large in the other two, 11 by 20 and 28 by 20. But there effectively were two-dimensional problems, so the only thing you had to determine was two parameters for each atom rather than 3. What we were after was the distribution of titanium versus niobium in the various metal sites through the structures. And here's the powder pattern for that one. And this is the powder pattern for the other one. This one's got something like 700 reflections in it, and this one had 800 or 900. I can't remember exactly which. Oh yeah, there we go, 600 and 800. Refinements took forever. We had to run them basically overnight. You know, one set of cycles overnight. Get this big stack of paper out for each one. And then the thing about it is that we did indeed determine the distribution of titanium and niobium. It turns out that's actually easy to do with neutrons because titanium has a negative scattering length. Niobium has a large positive scattering length, so they're radically different and easy to distinguish within the crystal structure. And found that most of the titanium went into a site which is, oh, I can't even remember where it is, but it's I think somewhere over there. In that case, somewhere like in here, for this case, which is right on the intersection of blocks of niobium dioxide block rock salt. So this was 1970 something or other, and a couple of years ago we got this paper from somebody who said, well, guess what? This stuff is in fact a potential battery material because it's easy to get lithium in and out of these structures. And so my comment is, but when somebody asks you, well, why are you doing something? The correct answer is you just never know, because we had no clue at the time. Okay, the history, this is the family tree of Hugo's problem of programs, which was, he called them pref and prof. And by the way, he originally wrote the programs in Algol, and that's what his 2 papers are based on, the Algol versions of his programs. He then later realized that nobody was going to use the Algol versions because it's a weird, strange, now dead language. So he converted them to Fortran. That's what he gave away. And in my view, that's why it's called the Rietveld method. It isn't really those 2 papers. It's the fact that he wrote the thing in Fortran and then gave it away to the world. And so that was the version that Alan Hewitt got, added anisotropic temperature factors, and then I got that one, and I had to deal with it with bigger structures because the programs as they stood would simply not fit in the computing facilities that were available. Well, this code wound up being the source of, I sent it to Ray Young at Georgia Tech because I had tried to put X-ray refinement in there and failed because I had no idea about the profile shapes. We had no idea. Well, Ray Young and his postdocs and graduate students sorted out what was going on there and wrote a version which ran on an IBM PC. And that then was the widespread distribution of Rietveld refinement around because then it was able to run on people's personal computers. I also took this same one and added neutron time of flight to it, or actually modified it to neutron time of flight. And that wound up at Argonne at the IPNS facility, which is where those superconductor structures were done. They were done with this version of the code. This DBW version of things then wound up being the ancestors of a whole bunch of other Rietveld refinement programs, including FullProf. And they revised it completely internally, but they used the same sort of language in the control file that Rietveld originally used. So you can see it basically in its DNA, if you like. Anyway, so that's the history. Well, here's a few examples. This is what Joel sort of alluded to about proteins. Proteins are large polymers of amino acids. They do all sorts of things that are absolutely essential for life, processing molecules of various kinds to keep us all running and growing or whatever. The structures can be described either as sort of balls and sticks like this, which shows, this one actually shows a molecule which has been captured by a particular protein. In this case, this is hen egg white lysozyme. And here's another one which is considerably larger. This is Botox. People sort of may recognize one way or the other. It's exceedingly toxic. And there are features which are sort of alpha helices, which are these things in red, and so-called beta sheets, which are these things where the ribbons do this kind of a thing instead of that. And then there are sort of random coil sections that join them all together. And this one is a so-called schematic diagram where the alpha helices are replaced by these sort of sausages. And then it's not shown in this particular structure because they don't exist, but beta sheets would show up as blue arrow, big blue arrows. Anyway, what does a protein powder diffraction pattern look like? Well, the shock was how sharp the peaks were. And how many there are. Well, we could anticipate how many there were. But this is a pattern taken at the APS hen egg white lysozyme. There is a ring down here, which is a 55 angstrom despacing, and it goes all the way out to about 1.8 angstroms, something like that. And there's 9,000 reflections. This picture doesn't even do justice to the original. It's really hard to get it show up properly. Despite the fact that there was some subtraction to clean it up a little bit, you had to take out the caps on sample, solvent, scattering, because this is a wet slurry of material, so it's got liquid in it. So that's taken out. And then there's air scattered, the fractometer. And despite that, there is a residual solvent scattering ring because a protein is around 40 to 60% water solvent, which is disordered, and it produces a ring somewhere around 3.5 angstroms. Right. Here's another pattern. This is a variation on insulin. Notice it starts at 8 degrees because this piece down here between 0 and 8 contains peaks that would go through the roof and somewhere up 2 stories up. It's just huge peaks at the beginning. But these things are just ridiculously sharp. They're sharper than this SRMs. Well, why is that? Because protein polycrystals are absolutely perfect. They have no defects. There's no strain broadening. They are around 1 micron, maybe 1.5 microns, something like that. So there's no size broadening to speak of. So you wind up with patterns that look like that. Okay. Well, in the process of doing the experiments, I did this particular one, which is what Joel was referring to, is that I had this particular version of zinc insulin, so-called T3R3. Don't ask me where these T's and R's and all that mean. It's all got to do with how the individual things look inside. And they have different pharmacological behavior when used. So this sort of thing is significant. Anyway, so I made up this stuff, ground up some single crystals, which is sort of horrifying to single crystallographers, but that's okay. And I got a pattern that looked like this. And this is kind of an ugly looking representation of it, but nonetheless, it looked like that. And for some obscure reason, which escapes me at the time now, is that I looked at that particular same sample again about 2 days later and had changed to that. So there was a phase change between here and here. And I took this stuff back to where I was at Los Alamos or Arizona State. It was Arizona, Los Alamos, and indexed this pattern. It isn't hard to index a protein powder pattern because the lines are sharp. The trick is you have to deal with the size of the unit cell. And the way you do this is that you take the D-spacing, divide by 10, in the peak positions, index that, and then remultiply the result by 10. Because an indexing procedure is scale invariant. It doesn't make any difference how big the cell is. It's all has to do with relative sizes of lattice parameters. So this one indexed to being A of 81, C of 73, and a rhombohedral space group. And this one was 81 on A, same as that, and 37 on C, which is half of that. So clearly this thing was doubled along the C axis. And that provided the clue as to what the heck had happened. Come on. There we go. So anyway, here's the powder pattern, and here is the sort of stick drawing of the crystal structure. The thing is enormous. The volume of the unit cell is almost 500,000 cubic angstroms. There's some 1,600 atoms in the unique part of the cell, which is this little piece here. And the Rietveld refinement, of course, gives something. And this is what happened, is that what you see here is superposition of two of these schematic diagrams of it. So there is one which is stacked on top of the other. And what happened in the phase change is that one rotated about 9 degrees relative to the other. So solving it basically was to determine that angle of rotation and how far apart they were, because they had shifted slightly in the distance. So it was a 3-parameter problem to solve crystal structure of an 1800 atom protein, or 16, whatever it is. And so I wrote all this up, put these guys on the paper and sent it off to my co-workers at the Hopman Woodward Institute in Buffalo. And they said, you scooped us, because they had found the same structure in a single crystal that had undergone a phase change because of the compression by the cryoprotectant stuff that they put around the crystals to protect it from evaporation. And that stuff had tracked it around the crystal and converted it from this single cell to the double cell. So there's the single crystal structure. There's the powder structure. It's basically the same thing. Okay. Now for something completely different, as sometimes we've heard. There is a station at the APS where the intent is to use the single pulses from the synchrotron to look at a dynamic process while it's occurring. So it provides a snapshot of the crystal structure as it's being, say, hit by a high-powered laser, which induces a big shock through it, high-pressure shock. So this was basically a test pattern of cerium dioxide positioned at the right place in this instrument, and they get a little powder pattern that looks like this. And when you do the integration around the rings, you get a powder pattern that looks like this. Notice that the lines are very asymmetric, and that's because the source is not a single sharp pulse like it is from an ordinary synchrotronic instrument where there's a monochromator that picks out one wavelength. This thing is a so-called pink beam, which has a spread in the wavelengths. And I looked at that and said, wait a minute, I know that line shape, because it's the same as the neutron time of flight line. So I said, right, let's fit this with the neutron time of flight profile function. And by the way, this experiment was done in 100 picoseconds. It's basically you take the APS synchrotron, put all the electrons into one pulse, and you gather the signal from that one so-called macro pulse. And that thing was 100 picoseconds long. Now, how short is 100 picoseconds? Light travels about 3 centimeters in 100 picoseconds. That's how short that is. So this is the fastest Rietveld refinement. Oh, there's the math. So there's 2 back-to-back exponentials. You're going to see this again when I talk about time of flight. Convolute that with a Gaussian, and convolute with a Lorentzian. This gives this thing involving something called the complementary error function. And here is the imaginary part of the exponential of something called P, which is somewhere down here, that. And the, let's say, I have to remember what this is, the exponential integral. So it's really sort of nasty little mathematics. But this all drops out of the convolutions. Anyway, and then you combine it into a pseudo void. And there's the fit, the Rietveld refinement of that data using that crazy function with a difference curve that's sort of within 2 sigma. And so this is fastest Rietveld refinement. seconds. Okay, inside GSAS-II. Joel gave you that. I apologize for the cough. I got COVID about a month ago, cured, but there's this leftover nasty, scratchy cough that I'm stuck with until it finally goes away. Anyway, this is the same function that Joel gave with all the same pieces. The only thing that's different is that because in neutron time of flight experiments, the powder pattern may or may not be normalized by the incident spectrum. In case it's not, then you have to have the incident spectrum itself in the calculation. Apart from that, it's all the same stuff. And I'm going to focus on the peak shape function. And we'll hear about some of this other stuff a little bit later. As is really worth pointing out, this is a more complex model than in single crystal crystallography. And it's one hell of a lot more fun because of that. Because there is so much that you can do with a powder pattern that simply makes no sense in single crystal. Joel covered this. So this is the same functions. This is the Gaussian, which generally arises from the instrument. So the combination of slits and monochrometers and whatnot, and the source itself in a single crystal in a powder diffraction instrument gives you a Gaussian line shape. That was actually sort of proved, I don't know, 1950 something or other by those three Italians, Cagliari, and I forget what the other two guys are, where the UVW stuff comes from. And the Lorentzian part is defined this way. This turns out to be largely from sample. And I'll tell you why that is in a few minutes. Now, properly, one should convolute these two together, and that convolution is known as the void. There is no analytic equation for a void. It simply doesn't exist. So what we use instead is a pseudo-void, which is a linear combination of the two. In the original descriptions of this thing by Ray Young and his associates, that's actually where it starts, back in the middle of EVWS. The mixing coefficient was a free variable. So that sort of meant that the Gaussian and Lorentzian contributions could be really screwy. Well, these guys, Thomson, Cox, and Hastings, formulated the mixing coefficient in such a way so that the pseudo-void equaled the void over all combinations of variables. And powder fractometers will suffer sometimes from a axial divergence because the slit that's used has a particular height. And so Finger-Cox and Jeffcoat created the appropriate thing for that. And both of these were installed into GSAS and GSAS-II. Okay, sample broadening. Well, this arises because the crystals that are used in powder diffraction are small. So the Fourier transform of the crystal size, which gives you what happens in reciprocal space, is not a delta function, but is a little broad peak. So you get a smearing of the delta functions according to the size of the crystallite. And this simply pushes through the arithmetic, and you get something called the Scherer equation, which looks like this. So smaller the crystals, the bigger the smearing, basically. Now, because there is a distribution of sizes, then the resulting diffraction pattern is the sum of sharp peaks and broad peaks and everything in between. And that gives you a Lorentzian line. If all the crystallites were exactly the same size, you get a Gaussian line, but they're not. In fact, you don't get that. You get a so-called sink function. But anyway, microstrain is the same sort of thing, except here, the supposition is not all the unit cells are the same size because of defects. It'll cause a slight expansion or contraction of the unit cell depending on the nature of the defects. And there's a distribution in those sizes. So you wind up with a Lorentzian distribution. But the point is that in this particular case, changing the unit cell will change the size in reciprocal space proportional to the distance from the origin in reciprocal space. So that one's close to the origin are small, one's farther away or large. So you get a different law for the broadening, which depends on tan theta. And if you put the units appropriately, then the units come out to be so-called microstrain units, which is 10 to the minus 6 strain. Okay. Yeah. Invite people to join you. Okay.
So you just,
Yeah,
just have easy.
If it doesn't get in my way, it'll be fine. This is an awful lot. By the way, all of my slides will be available to you, whenever. So you can study this one if you wish. But this basically shows how the Lorentzian components and Gaussian components are mixed together to give you the components that are actually used in the profile calculations. And it allows for the possibility that there could be some Gaussian sample broadening or some Gaussian microstrain broadening. It's very rare that you encounter that, but the availability is there. Okay, in GSAS-II, what we have done is to separate the instrumental contribution from the sample contribution. There are different places in the code. They are applied differently. They have different rules for their use. So the instrument parameter coefficients, whatever they happen to be, are established beforehand either by you by running standards or by your instrument responsible by running standards on their synchrotron or neutron scattering instrument. And they provide these things to you. And they wind up here. And this is where you'll find UVW and XYZ and all those kinds of things that characterize the Gaussian broadening from the instrument, plus whatever else is associated with the instrument. Things like the wavelength, and polarization, and the axial broadening term. And these things usually describe a nice parabola, and there's a bit of graphics that shows up. When you display this, the graphic shows the resolution curve. And so when people talk about the resolution of their instrument, it's this that they refer to, because the sample broadening is then put on top of that. Over here, under phases, which is this little piece here, and by the way, my next talk, which is going to follow this one immediately, I'll talk about this stuff in detail. But there is the sample broadening terms are defined here as size in microns or microstrain in 10 to the minus 6 strain units. And there's a number of different models for each one of those, and you can then display what the shape of that microstrain surface is or the particle shape surface is. Okay, time of flight. You've actually seen this function earlier because the same one was used for the pink bean thing. But here it is, the original one for, in fact, actually, this guy here is the original one for neutron time of flight for Gaussian broadening. And then this is the piece for the Lorentzian term. These things arise from the convolution of a rising exponential, decaying exponential against a Gaussian and a Lorentzian. And you get a whole lot of coefficients, mostly of which were established by empirical means based on an analysis of individual peaks. One important point about these functions is the peak top is not the peak position. Peak position is always shifted to the sharp side of the peak. And that's a little bit counterintuitive. But if you think about that thing convoluted with a symmetric function, peak top is going to be, the peak position is going to be on the sharp side, because that's where it is here. I mean, it's just going to follow. But, you know, if you do things like phase analysis and all that sort of stuff, or lattice parameter determinations with data which is asymmetric because of this kind of effect, you have to remember that the peak position is not the peak top. Shift. Okay. So similarly, the instrument parameters for neutron time of flight are here. There's a whole lot more of them because you had all those alphas and betas, sigmas and whatnot, and different diffractometer constants. But you get the same kind of resolution curve shown to you. And the sample broadening stuff is identical between the two cases because this has got nothing to do with the radiation of the experiment. It's all got to do with the sample. So ideally, if you took a sample and looked at it with tau gen at SMS, and then the diffractometer out here, then sample broadening ought to be the same for both experiments. Ideally. Sometimes, mostly is. Okay. What's next? All right, one last little thing about this part is how do you get out structure factors? Well, if you integrate across, if you sort of do the profile fitting across the peak, but you save how the individual contributors make to that peak, you can then integrate the contributions from each reflection and get an integrated intensity for each structure factor. So that's what's done to get out structure factors. And why do you want structure factors? Well, they're the only thing you've got if you want to calculate a Fourier map. You need them for that purpose. There's two other ways of getting at them. One is the so-called refinement of the profile coefficients of the structure factors themselves, and the so-called Pauli refinement. That's what this one is. And then there's another method called the Levi method, which is similar but different, which is a cyclical kind of thing that calculates the structure factors. But the extraction process is up here. And right. Okay, simple example. And this is the subject of one of the tutorials as part of GSAS-II, which is to do a refinement of fluoroapatite. Now you may ask, where did this example come from? Well, this was Ray Young's original example for DBWS. It's the same data set. It's like 50 odd years old, collected on a laboratory diffractometer that was at Georgia Tech. And there's the powder bed. So the way you do a Rietveld refinement is you have to put in all the atoms and the lattice parameters and the space group information. And while you're doing that, GSAS-II will collect the structure, the form factors, everything else that's necessary for doing that. And then you do an initial refinement, in which you try to find out what the scale is, because you have not any idea what it is, and the background. And then you wind up with a curve that looks something like this, which is a horrible fit. And the way you get through this is you have to notice what the shape of the difference curve is, because that gives you the clue as to what to do next. Right. And here are the three things to look for. Is that, first of all, if there is a difference curve signature that looks like a first derivative, where it goes up and then down and then back to level. And this is a little complicated here because this is alpha 1 and alpha 2 laboratory diffractometer data. So you get two signals and superimposed on top of each other. So this is a sort of feature, and that's because the peaks are in the wrong place. When the peaks are in the wrong place, it's probably because either the lattice parameters are not correct or there's a sample displacement. The next thing that can happen is if the sample broadening is incorrect. Now, the instrument parameters will give you the sharpest lines, calculated lines. The sample broadening will give you sample peaks, which are broader. So the difference between the two will look like a second derivative curve. It'll go up and then down and then up in the middle and then down on the other edge like that. So it goes up, down, up, down. Now, it could conceivably be the other way around. If you made a guess at the sample broadening and you guessed it too large, in which case this would be flipped. So in this particular case, it's because the size is too large, but it also could be because the microstrain is too small. The third possibility is you simply get the wrong intensity on the peak. So this is basically the difference curve will look like a peak, either plus or minus. And that's because you got something wrong with the crystal structure. Or you've got some sort of correction which corrects for something in the intensity, like absorption or extinction or something, or texture. So that, with those clues in mind, you then look at this pattern, you blow it up so that you can actually see what the difference curve looks like, and you look at it, and lo and behold, it's mostly that second derivative, with maybe a little bit of position error. So what you do is you put in the microstrain parameters and the lattice parameters, and you do the refinement, and you get sort of instant gratification because it fits a lot better. And then you look at the curves, and it's mostly because the intensity is wrong. So therefore, something's wrong with the crystal structure. So you put in the atoms next, wherever this is, and the temperature factors, and it winds up with this. And by the way, you'll never get rid of all of it. It just doesn't happen. There's always something left over. And that's sort of part of the mystery of the Rietveld refinement, is you can never get the fit perfect, although I've seen it occasionally happen. So the major errors in the initial model were peak shapes, because the sample displacement, sample broadening, and then there was an error typically in the sample displacement of the lattice parameters, and then some subtle things having to do with atom decisions. Okay, I think this is the last plot for this particular talk. One of the things that GSAS-II produces is a view of the covariance matrix. Now, I didn't go through least squares theory, but you build this matrix, you invert it. That inverted matrix, the diagonal tells you how much to shift the parameters. It also tells you what the errors are in the coefficients. The off-diagonal terms tell you how one variable depends on the so-called covariance. And when you look at this plot, yellow is no covariance at all, based on the scale. Red is a negative covariance, and green is a positive covariance. So you'll have a scattering of high correlation sort of terms here and there associated with those. This is really only useful if those covariances turn out to be very close to 1, which means that the two parameters are highly correlated. All right, and thank you for that. That becomes a difficult one. Any questions?
So I want to say the
You're gonna have to shout because I'm dead.
niobium paper
Yeah.
you're mentioning about batteries. That's my professor.
Yeah.
So he's got more work on it. By the way, we're continuing to work on.
Well, I'm kind of wondering about it. Haven't
Yeah,
seen a car
I can
advertised with
share
it.
stuff with you later. Yeah, there's some cool stuff in the space, but definitely inspired by those Newton papers.
Yeah.
Yeah.
So you actually managed to find it.
Yeah.
More questions?
Any other questions?
Remember that there is no silly questions, right? We want